Hello everyone, this is Doug, and in this video I'm going to introduce you to acids and bases. So first of all, right, acid-base chemistry is everywhere. You've already kind of looked at acid-base reactions in an earlier video, but I just want to mention, right, you see stuff in your home all the time. I don't know if you were ever lucky enough when you were a kid to do those vinegar and baking soda volcanoes. But you do it all the time if you ever make biscuits or cookies, right? You use like baking soda and stuff like that. That's all acid-base chemistry. You may hear pH balanced on like a shampoo or something like that. That's has to do with acid-base chemistry. Your household cleaning products, right? Whether it's your relatively basic window cleaners or your relatively like acidic things like CRL if you're using it to get rid of rust or something like that. But you also hear about acids and bases in terms of your environment, right? So you've heard of like acid rain, or maybe lately things like ocean acidification or soil acidification, right? So acid-base chemistry is also really important for the environment. I have a little graphic over here, right, with the acid rain idea. We don't have as much acid rain in this country anymore because we've regulated what can and cannot be burnt. But it used to be, right, that our factories would burn things like that have nitrogen or sulfur in them, and so they'd make these NO2s, NO3s, stuff like that. And the problem was that they would then combine with water in the air to make acids, so like nitric acid and sulfuric acid. How do I know they're acids? One way to kind of tell is that oftentimes when things start with H, those suckers are going to be acids, because we'll talk about here in just a second that acids are things that donate hydrogen, H plus specifically, the hydrogen ion. And then that, of course, that acid rain had all kinds of negative environmental effects. It would just kill trees and destroy forests. It would help dissolve things like statues, which is not really that big of a deal. You just have one fewer statue in the world. But it would also lower the pH of certain kinds of lakes and ponds, and the aquatic creatures didn't like that and would die also. So in our country, we've pretty much regulated the amount of nitrogen and sulfur that you can burn in things like coal, and so we don't have that problem anymore. But this is still a problem in a large part of the world, and if we ever deregulated, what types of things we can burn, then it would come back for this country. But we're not going to talk about the at-home applications or the environmental applications, right? We want to talk about what's going on in the body, what's going on in biology, right? So biological. Right? You've probably heard of things like stomach acid or maybe your blood pH. pH is talked a lot about in sort of like natural medicine, sort of fringy, sciencey kinds of groups. And then things like acidosis, metabolic acidosis, or respiratory acidosis. So we want to have some sense of what's going on in the body in terms of acids and bases. So we're going to just kind of have a brief introduction on what acids and bases are in this video, and then in future videos we'll talk a little bit more about buffers, like the blood buffer system and the cell buffer system, and just what the pH scale means. What is a low pH, what is a high pH, what does that have to do with our body fluids, etc. So first, let's talk about acids. There are a few different definitions of acids, like the Arrhenius and the Lewis. The most common one, though, is what's called the Bronsted-Lowry definition, whereas all it means is that you donate a proton, an H+, right? So here's your proton. Or you can also call it the hydrogen ion. Right, or you could say the hydrogen ion, right? It's literally just a proton, because remember that hydrogen only has a proton in its nucleus and one electron, and if it loses that one electron, then we're talking about just a proton here. And the abbreviation for the acids are often just HA, where the H is going to be the H plus that is going to lose, and then A is just the rest of the molecule. So it's the rest of the acid. And you'll see reactions like HA turns into H plus and A minus, right? That would be an acid breaking up or dissociating. They kind of dissociate like we would say an ionic compound would. Some biological examples would include things like hydrochloric acid, right? So good old HCl. Hydrochloric acid, so HCl, hydrochloric acid. This is the stuff, you might recognize this. This is your stomach acid. Right, our stomachs tend to have pretty low pHs, but the acid that we have in our stomach is the hydrochloric acid. And so if I wanted to show the hydrochloric acid dissociating, right, I'd say HCl turns into H plus and Cl minus. So here is the idea that HCl can donate an H plus. It can give up that H plus, right? It starts with an H plus. I could also look at carbonic acid. That's going to be a really important one for us. So carbonic acid is H2CO3. Carbonic acid is super important because it's the combination of carbon dioxide, which we make all over our bodies and in our cells, interacting with water makes carbonic acid. So we see carbonic acid in like all of our fluids, all of our the fluids that are inside and outside anything that's metabolically active, basically. And so carbonic acid can also dissociate, where it can give up one of its H pluses, and then you have bicarbonate afterwards, which also could be an acid and could give up the H in carbonic acid also, or in bicarbonate. But carbonic acid dissociates to give H plus also, and then bicarbonate. So I'm just splitting these up. I'm just taking the H plus off of these molecules. Another important acid in biological systems are the phosphates, and I put that in quotes because, right, a chemist would say that phosphate is PO4 minus 3, but in biology, when you talk about like cell biology and stuff like that, when they say phosphate, what they really mean is two different species. They mean both the HPO4 minus 2 species, and they mean the H2PO4 minus 1 species. And that's just because these are in equilibrium with each other, and they're in a roughly 1-to-1 ratio at normal pH, like a pH of about 7 or so. So when people say phosphate, they really mean like both of these. But the idea here is that these phosphates could act as acids also, and we'll see them behave in buffers here in a second. But because this is H2PO4 minus 1, I could, in theory, have one of those hydrogens pop off to give me an H+, and then I'd be left with just one H and the PO4 minus 2. So PO4 minus 2, right? Where once again, I'm just giving up an H+ is the idea. And I could have done the same thing with the other one. And then lastly, the carboxylic acids, right? We have carboxylic acids. This is going back to our carboxyl groups, our organic things, right? If you have any kind of carbonic or carboxylic acid, so let's just say this little sucker, this little thing that looks like, kind of like a tiny fatty acid, the idea, right, is that these carbonic acids could dissociate to give the O minus and an H+. And we've seen that when we talked about amino acids, for example, right? Remember we said that the carboxyl in amino acid pretty much just dissociates in physiological conditions. So we can write the carboxylic acid as acetyl-1-O with OH, or we can draw it without that H. We can just have the O minus, which we also did, right, in the ionized version. So carboxylic acids can also act as acids. The big thing I want you to get out of this, right, is that the acids are things that donate protons, which means they have to have H's, right? They have to have H's in front. So typically, and it's in front, sorry, I should mention that, right? A good way to spot an acid is if the formula starts with an H. So you notice that for hydrochloric acid, right, we started with an H. For carbonic acid, it starts with an H. Phosphate, these phosphate formulas starts with an H, starts with an H. The carboxylic acids are organic, so it's a little bit weirder to draw out, but we should remember that the carboxyl groups, they're called carboxylic acids, so that should be a good reminder that they're acids. They donate H pluses. So these are common ones that you're going to see throughout if you take A&P or something like that in our class. I just want you to be able to kind of spot them. Just know that they're things that donate protons. And if you go back to our acid-base reactions video, right, we talked about acids are just things that donate protons to something else. So I'll pair these up in a little bit here, but here are just some common examples of biological acids. So some examples of bases. I've got Bronsted-Lowry definition of bases. It's just something that accepts a proton, something that picks up a proton. So sometimes we write things like, oh, well, if you have a B minus and an H plus, right? The idea is that that thing, this is supposed to be the base, that thing can pick up the H plus and they'll bond together to give you an HB, where this is now what the conjugate acid that it makes. So just generically, you might see like a B minus or something to stand for some super generic base. The common biological examples of bases would be your hydroxides. So people have heard about Li, like sodium hydroxide or magnesium hydroxide or calcium hydroxides, just some sort of hydroxide. And the idea here is that if you have H plus and you have something like sodium hydroxide, this hydroxide can pick up the H plus, and it's going to give us HOH, or in other words, water, right, H2O. And so the idea here is that your hydroxide is going to go pick up your H plus. It's going to react with the H plus. So now your hydroxide has one more H on it. It's accepted that proton. It's accepted that H plus to now give you, in this example, water. Same thing with all these other examples, right? The bicarbonate example. carbonate or bicarbonate, right? So remember, bicarbonate is HCO3 minus, carbonate is CO3 minus 2. You could imagine, right, an H plus, and let's just use carbonate in this example, right? If these combine, right, if you have carbonate pick up that H plus, now it's just going to be H CO3, and now it's no longer minus 2, it's minus 1, because a negative 2 and a plus 1 make negative 1. So this would be an example, right, of the carbonate picking up that H plus. Phosphates, again, right, those phosphates, same thing, whether you're talking about HPO3 minus 2, or you're talking about PO4, not 3. Let me fix that one. PO4. Same thing. They can also pick up H pluses, right? So I can have H plus, and I can react that with, here, let me write this out. Sometimes I have pen malfunctions. Let me fix this here. All right. H plus and PO4, let's see, the minus 2, 1. Right, that can pick up that H to now give us H2 PO4 minus, right? So I just had it pick up that other H plus. Just the point in all of these, right, is that we are we're simply just picking up an H plus, right? It's just a basis, anything that can just pick up a hydrogen. That's the idea. And then just like we had carboxyls as an example of an organic functional group that was acidic, remember that amines were an organic group that was considered to be basic. So I could draw some sort of amine and an H plus, and that will combine, right? These can pick up hydrogens also. These also can pick up H pluses to give us a new product, namely the ionized version. And again, we saw this when we talked about amino acids, right? We said that the NH2 would turn into an NH3 plus in physiological conditions because amines are bases. So here are just a few examples of biological acids and bases, right? Remember just that the acids are the thing that accept, or the acids are things that donate the protons, and bases are things that accept a proton. I definitely want you to be able to identify what an acid is. It's super easy. I mean, just standalone. It's super easy to identify just an acid by its formula because they start with hydrogen, right? If they start with hydrogen, they can act as acids. Bases are harder to identify, so I'm not going to ask you to identify them. I don't want you to just like memorize a list of bases, but here's just some common ones that you're going to see. I guess I should have mentioned, where you're going to see these a little bit more. The carbonate bicarbonate, you're definitely going to see a lot in the blood buffer system. Things like phosphates, you see these all over the place, but definitely really important in the intracellular fluid, so inside cells. Inside cells, the phosphate buffer system is really important, so you see phosphates picking up and dropping off H's all of the time. And then amines are just really, really common throughout, right? Very, very common. Remember that you're mostly made out of proteins, and proteins all have amines in them. So you're gonna have amines all over the place. So your proteins are definitely going to be an important part of a buffer system. And remember that proteins are susceptible to changes in pHs. It makes them change their shape, and they can get denatured and stuff. And that's because you can pronate or depronate these amines. So, anyways. I want to show you one example of a acid-base reaction, just to kind of put this in a little bit more context. So let's look at these two examples, right? Again, this is kind of a flashback to the acid-base reaction we were talking about before, but remember that acid-base reactions are just a transfer of a proton, right? Acids give protons, bases pick up protons. So you can have kind of this sort of classic example where I have HCl, so maybe this is from like stomach acid. So let me put like stomach acid. Right, and let's say you've got some heartburn or something like that. You might take something like an antacid. So here would be magnesium hydroxide. That's from an antacid. So stomach acid is HCl. MgOH is like milk of magnesia. Milk of magnesia. Which you can just buy at the drugstore or whatever, which is magnesium hydroxide. And the idea here is that we do an acid-base reaction, right? If I just had to guess just right off the bat which one of these is the acid, aside from the fact that I labeled this stomach acid, we should be able to identify that HCl is the acid because it starts with an H, right? This is the acid because it starts with hydrogen. It starts with hydrogen. And we're going to see that it's going to be the thing that donates an H+. Right, so let's see if we can convince ourselves that donates an H+. Right, if I take a look at this, HCl, right, HCl, it's like I have an H+ and a Cl-, and it's like magnesium hydroxide is an Mg2+ and 2 OH-. And if I look at the products, sure enough, I've done that sort of double replacement. I've switched the two things, right? So now it looks like I don't have hydroxide anymore, right? I don't just have OH-. Now I have an extra hydrogen on there. So it's like these hydroxides picked up these two hydrogens, right? Remember, I have a 2 coefficient. So it's like these hydroxides picked up these two H+. So the HCl donated an H+ to the hydroxide, which means the hydroxide must have been acting as a base, right? If it accepted the hydrogen, then this must have been the base. So all the hydroxides must be the base because they accepted that H+. So we should be able to identify what's the base and what's the acid if we're given a formula, right? The thing that gives off the H+, that's the acid. The thing that accepts the H+, that's the base. And remember that I said hydroxides were an example of a base. I can have a more organic-y example here, right? So if you take a look at these two, it looks like this H got transferred onto the phosphate, and now it's over here. So I've transferred that H from one molecule to another one, which is how I know it's an acid-base reaction. And I need to just figure out which one's the acid and which one's the base, right? So it looks like the phosphate picked off this H+, and now we've transferred it here, right? So if I want to know which one's the acid, I just want to know which one donates the H+. It looks like this is the thing that had the H+, so this must be our acid. And actually, I'm going to use the same colors just to be consistent here. A little consistency. This must be the acid because it donated the H+, because this is the H+ that was donated. And then the other thing, right, the phosphate must, in this case, be acting as a base because it accepts the H+. Right, because it accepts that H+. Right now it has the H+ over here. It picked up that H. So we're not going to go crazy. You're not going to see a bunch of crazy reactions, acid-base reactions. But here's just your simple introduction. This is really all I need for you to know to be able to start to understand some things that are going to happen in cells. If you have any questions or comments, please leave them down below. Happy studying, and keep an eye out for my buffers video and my pH video. Take care.